Welcome back. In this video, we'll learn about multi-layer perceptron in detail. Multi-layer perceptron consists of one input layer, one output layer, and one or more hidden layers. Here, neurons in each layer are fully connected to all neurons in next layer. You can see here, A is connected to all neurons in the next layer. Similarly, B is connected to all neurons in the next layer. Here, the information flows in both the directions, in forward direction as well as backward direction. Backward direction is also called as back propagation. In forward direction, the inputs are multiplied by the corresponding weights. Weighted sum is passed through an activation function to produce the output. Whereas in back propagation, errors from the output layer are propagated back. Weights are adjusted to minimize the error. First one, forward propagation. In forward propagation, the data flows from the input layer to the output layer, passing through the hidden layers. Each neuron in the hidden layer processes the weighted sum as well as the activation function. The weighted sum is nothing but the neuron computes the weighted sum of the inputs. We all know that Z is equal to summation of I Wixi plus B, where B is the bias, Xi is the input feature, Wi is the corresponding weight. Activation function. In the activation function, the weighted sum Z is passed through an activation function to introduce a non-linearity. Common activation functions are sigmoid function and ReLU. The next one is loss function. The next step is to calculate the loss. It means that the error after the network produces an output. The loss function is the difference between the predicted output and the actual label. In supervised learning, the loss function compares predictions as well as the true labels. For any classification problem, a commonly used loss function is a binary cross entropy loss. It is represented as L is equal to minus 1 by n sigma of I is equal to 1 to n yi log yi cap plus 1 minus yi log 1 minus yi cap. Here yi is the actual label. Yi cap is the predicted label, where n is the number of samples. For any regression problem, the mean squared error is often used. We represent the mean squared error as MSE is equal to 1 by n summation of I equal to 1 to n yi minus yi cap square. You know that what is yi and yi cap. The next step is back propagation. The goal of training an MLP is to minimize the loss function by adjusting the network's weight and biases. This is achieved through back propagation. It actually works with the gradient calculation, error propagation, and gradient descent. So we'll see what is gradient calculation. The gradients of the loss function with respect to each weight and bias are calculated using the chain rule of calculus. In error propagation, the error is propagated back through the network layer by layer. In gradient descent, the network updates the weights and biases by moving in the opposite direction of the gradient to reduce the loss. And it is represented as W is equal to W minus eta into dou L by dou W. Here, W is the weight, eta is the learning rate, dou L by dou W is the gradient of the loss function with respect to the weight. The next one is the optimization. Multi-layer perceptrons always rely on optimization algorithms to iteratively refine the weights and biases during the training process. Popular optimization methods include stochastic gradient descent and Adam optimizer. We'll see what is stochastic gradient descent. This updates the weights based on a single sample or a sample batch of data, which is represented as W is equal to W minus eta into dou L by dou W. What is an Adam optimizer? This is an extension of stochastic gradient descent that incorporates momentum and adaptive learning rates for more efficient training. We represent the momentum as mt is equal to beta 1. Beta 1 is decay rates, then beta 1 into mt minus 1, that is the momentum in the previous iteration, plus 1 minus beta 1 into gt. Gt is nothing but the gradient at time t. Then Vt is equal to beta 2 Vt minus 1 plus 1 minus beta 2 into G2 square. Here the beta 1, beta 2 represents the decay rates and Gt represents the gradient at time t. Thank you.